Welcome to third video on analog to digital converters. So we shall consider the transfer characteristics of a 2-bit ADC. So we know that 2-bit ADC has got 4 output combinations, that is 0, 0, 0, 1, 1, 0 and 1, 1. So we are plotting the input voltages of 4 different levels. So one is 0, the other one is 1 by 4, 2 by 4, 3 by 4. Now the LSB is now actually V full scale range divided by 2 power n. Since n is equal to 2, it is now considering the full scale range is 1 volt. 1 by 4, 2 by 4, 3 by 4 and 0 are the 4 different levels. We are assigning 0, 0 as the output voltage for input voltage ranging from 0 to 1 by 8, that is half LSB, from half LSB to 3.5 LSB, which is another output level, that is 0, 1. For 1, 0, it is from this is a voltage which is, this is 1 by 4. So this happens to be, of course, which is 1 by 8, 2 by 8. This is actually 3 by 8, 3 by 8 to 5 by 8. So this is the voltage level, that is the output level that is assigned for voltage ranging from here to here. As we can see here, the quantization error is actually 0 for 0, and it's again 0 for 1 LSB, 2 LSB and 3 LSB. So the quantization error is maximum for half LSB, 1/3 LSB, and it's half LSB, 3 times a half LSB and 5 times half LSB. So this way we can able to write the transfer characteristics and the quantization error graph for a 2-bit ADC. Now this is again the transfer characteristics for a 4-bit ADC, where we are having 16 possible inputs starting from 0 to 15 by 16, and we have 16 output combination starting from all 4 zeros to all 4 ones. So this is the quantization error. So there's a slight offset in this, so just manage that. So we're going to have 0 error when it is 0, and when it is moving over here, now you can see it is the maximum negative error, this is the maximum positive error, and you can see the error happens to be 0 for every LSB. Let us try to identify what is this INL for ADC. INL, as you know, that it is integral nonlinearity error. For that, let us take a 3-bit ADC. We know that for a 3-bit ADC we have 8 different input combinations starting from 0 to 7 by 8, and we have correspondingly 8 different output combinations starting from 0, 0, 0 to 1, 1, 1. Now this is the ideal transfer characteristics. This is one of the typical characteristics. As you can see, this width is not always 1 LSB. So whereas in case of the ideal case, the output voltage will be a particular output, that is 001 for 1 LSB length of the input voltage. But as you can see here, this is not exactly 1 LSB, it is keep on changing here. So this line, that is a slope of line which is of 45 degree, is actually passing through just a minute. It is passing through the center point, midpoint of all these actual code ranges. So this is the code range. So it is passing through the center of all those code ranges, and we have a typical ADC characteristics. Now this dotted line, as you can see here, the dotted line represents the locus of midpoints of the actual code ranges. So we have this is the code range. Now the code range is not exactly 1 LSB, it is sometimes half LSB, sometimes it is 2 LSB, sometimes it is 1.5 LSB, sometimes it is again 1.5 LSB. Now this dotted line actually indicates the locus traced by the midpoints of this actual code length. So this is the dotted line which is stated here, the dotted curve representing the locus of midpoints of the actual code range is now called as code center line. So this is the code center line for the actual one. For the ideal one, this is the code center line. Now let us try to find out its maximum deviation from the straight line passing through the endpoints after the offset. I can see here we don't have any offset error and we don't have any gain error. So after nulling the offset error and the uh, gain error, so we are plotting this core center line. You can see there is a maximum deviation happening. Its maximum deviation from the straight line passing through at the ends after the offset and the gain errors have been nullified and is called as. So wherever we have a maximum deviation from the actual core center line to the ideal core center line, so it is called as INL. So even in case of the DAC, we actually found out uh, from that ideal line where exactly the actual output voltage is there. Here also we are looking at the difference from the actual core center line to the ideal core center line. Let us try to find out what is DNL of a ADC. So, and of course, a DNL will result in a missing code. We should try to understand what is this missing code and all those things. So, ideally, the code transitions are one LSB apart. As you can see now, so there is a code transition happening at one half LSB, and there is one more code transition happening at 3 half LSB, 5 half LSB, meaning ideally the code transitions will be always apart by 1 LSB. But as you can see in this particular typical example, so there is a code transition happening at this point. The next point is happening over here. Now the length of this code is not actually 1 LSB. It is more than 1 LSB. So here you can see it is less than 1 LSB. Here it is almost 2 LSB. Now the maximum deviation from the ideal value is called as differential nonlinearity. So now we can see there is a DNL of half LSB, because here we don't say there is a DNL because all the codes are having a length of 1 LSB, but here we have a DNL of 1 half LSB, because it is 1.5 is the length, but whereas what is required is actually 1 LSB. Now the DNL of this particular input combination, that is the output of 001, we have a half LSB DNL. Here it's actually minus half LSB. Here you can see there is a DNL of 2 LSB, because expected is 1 LSB. We are having actually 2 LSB. And it is surprising to see, of course, we can see there is no code available here at all. So that's what we call it as a missing code. The maximum deviation from this ideal value is called as differential nonlinearity. The ideal value happens to be 1 LSB. If the DNL exceeds 1 LSB, some codes may be skipped at the output. So as we can see here, this is maybe. Now here the DNL is actually this is actually exceeding. Now we can see it is actually exceeding 1 LSB. Now it is almost 2 LSB. This length is actually 2 LSB. So because it is 2 LSB, there is a possibility of code being missed out here. Now let us see what happens. Missing codes are undesirable in a digital control where they may lead to instability. So actually we want to have 0, 1, 1, and then we want to have next bit as 1, 0, 0, 0. So instead of getting 1, 0, 0, so we'll be missing that code because this DNL is more than the ideal value. So let us again continue with the same DNL and missing code. The INL error is maximized in 0, 1, 1. Okay, as you can see here, so in this 0, 1, 1, so as you can see here in this 0, 1, 1, the amount of deviation from the ideal line to the actual line. So this is the lines joining the centers of the code. So this is the actual dotted line which is actually passing to the center of the code length. So here exactly the deviation is more. So you can see the here deviation is less, the deviation is less at a given input voltage. The deviation is maximum only for this 011 code. For 011 code, you can see there is a maximum deviation. So this error is actually almost half LSB. Now you can see this is half LSB here. this range also maximizes the DNL error. So wherever we have INL error maximum, so this range also maximizes the DNL error. The range width of this 2 LSB indicates. Now you can see this is the range width. The range width is actually 2 LSB. So when it is 2 LSB, actual DNL happens to be now 2 LSB minus 1 LSB, because 1 LSB is the minimum code length we're going to have. Since we have a code length of 2 LSB, the DNL happens to be 1 LSB. So not surprisingly, there is a missing code. As we can see here, so this is the code length which is actually 2 LSB, which results in a DNL of 1 LSB. So whenever we have maximum deviation in terms of INL, so there exactly we're going to have more DNL also. So this DNL more than 1 or close to 1, we're going to have a missing code. Now you can see we are having a missing code because the DNL is actually almost cos is equal to 1. So now here the DNL is half. So this is not giving a missing code. We are still representing it by 0, 1, 0. But here, since the code length is 2 and it is resulting in a DNL of 1 LSB, we'll end up with a missing code. So we should always ensure that DNL doesn't go close to 1, so that we're going to end up with a code that is missing out. After seeing the INL and DNL of the ADC, we know that once we give the startup signal, the ADC will going to complete that operation of converting that input analog voltage to the digital form. It will certainly take some time. So that is represented by the conversion time. An ADC conversion takes a certain amount of time to complete, called the conversion time. It is typically ranging in the form of less than 100 nanosecond to tens of millisecond. So it will be ranging from, of course, nanosecond to milliseconds, depending on the conversion method and resolution and the technology that we are using. So usually the conversion time is not too high, so it ranges from tens of millisecond to, of course, it will be as small as tens of nanosecond. So let us see what is the effect of this quantization error. A practical ADC will produce noise in excess of the theoretical quantization noise. So we saw that the quantization of noise is half LSB maximum and minus half LSB minimum. So we can see the peak to peak quantization noise is almost 1 LSB. So along with that, we're going to have some other. So that is the theoretical quantization noise. So because of the semiconductor components that are used for producing the ADCs, there are some other practical noises that will be affecting the quantization. It will also introduce distortion due to the transfer characteristics of characteristic nonlinearities of the transistor, where you have a resistor, semiconductor, transistors, op-amps, all those things. The effective number of bits is given by. So as you can see now, the ENOB stands for the effective number of bits is given by signal to noise ratio. This is signal divided by noise plus distortion minus 1.76 dB divided by 6.02. So where this signal divided by noise plus distortion is the actual signal to noise ratio plus noise plus distortion is ratio in terms of dBs. So in the earlier case, we saw that there is a signal to noise ratio. That is the ideal case. In the practical case, we're going to have some distortion also. So there's a distortion noise is also included here. So the effective number of bits is given by this particular equation. We shall take up an example and try to find out. So there's a 10-bit ADC with so and so specification. These are the equations governing the EQ, the SNR max, and ENOB. Now we are asked to find how many number of bits, even though it is 10 bits. So we'll be getting 10 bits. So actually, when you actually find the effective number of bits, even though it is 10 bits, because of this increased signal to noise ratio plus the distortion, so effective number of bits is actually 9.01. We're going to actually miss 1 bit in this 10-bit ADC. Effectively, we're going to get only 9 bits instead of 10-bit operation. It's because of the increased noise due to the distortions. So this way, this noise due to the distortion will also be affecting the number of